The next thing I want to talk a little bit about is the ISIS out-of-band data transfer technology. It's something that we introduced kind of recently. The issue is the following. ISIS at the beginning didn't turn out, when we first built it, didn't turn out to be very good at dealing with large objects. And so we did a lot of work internal to the system on taking big message objects and cutting them into pieces and transmitting them. But we found that frequently the system got kind of constipated. You'd have a situation where one task was transferring 20 megabytes. Some other task had just a couple of bytes and they wanted to interact with the same group. But the couple of bytes might easily end up after the 20 megabytes, and the latency for sending that little query or that little multicast would turn out to be dominated by the time that it took ISIS to push the 20 megabytes through the system. And then we began to talk to people with big data applications, and they said, well, 20 megabytes is nothing. We're going to be using external memory mapped files that have gigabytes in them. So we thought about that and realized there was no way that the internals of ISIS were ever really going to be a good way to handle moving gigabytes of data around. So it occurred to us that what we could do is suggest to people that would have very big data objects that they should deliberately store the big data objects in memory mapped files. Okay, what's a memory mapped file? It's a normal file, but you tell the Linux or the Windows file system that you'd like the file to be available directly at the speeds of the computer memory, and that's done by sort of paging the file in using the virtual memory system. It's very, very easy to set up and very fast. In fact, you'll see some examples of it in this slide set and more examples in the ISIS manual. And then what we could do is we've realized we could have the ISIS system talk about the file names instead of the files. You could multicast the name of a memory map file. And we built this feature into ISIS that would transfer the data in the memory map file from place to place at much, much higher speeds than what we're able to do within the system. Still reliably, so you get your data intact, secured. In fact, we encrypt this data if you ask us to, and we'll move it from place to place according to the data pattern that you request, and you can dynamically change the pattern. And so you can start to imagine a world where a collection of machines has some large numbers of these huge files, and now they keep using ISIS to orchestrate shifting the data around in different patterns with each different file being moved, and that can be done in real time. And what ISIS does is it tries to optimize the transfers to come as close as possible to 100% utilization of the Ethernet or InfiniBand connect that might be there, and it tries to use multicast if that feature is available. So if you have a very large file and you want to make 100 replicas of it, rather than copy it 100 times, ISIS will blast it out with one copy going to 100 receivers, and then if some of them dropped a packet here and there, it fills in the gaps. It's done with a very, very efficient, simple protocol. And what's nice is because it's out of band relative to the core ISIS system, meaning it's happening off on the side, the core ISIS system maintains its snappy performance, and you don't get this problem of the guy with the 2 bytes stuck behind the guy with the 20 bytes, or in this case it might be hundreds of gigabytes. So it's for applications that are working with fairly large objects, but how large is an object? It turns out that as we got this working, we began to discover that it's actually advantageous to do this even if you're working with as little as a few hundred bytes if the group is large. And so for an example, in ISIS itself, when a membership change occurs in a large group, we send a delta and we just say, process P joined and process Q left. But if large numbers are joining, we have to initialize those members. And in that situation, suppose that we had 50 or 100 members joining a group that already had 1,000 members. We realized we were sending tens of megabytes of group view information to those members. We started using the same out-of-band transfer for that, and dramatically improve the performance of the system itself. So ISIS even uses this approach internal to the system. Right. Now, why, by the way, is ISIS so slow at doing large transfers? So the problem is that, well, for state transfers and for views, we're using point-to-point communication, and for multicast, we're using multicast. But in all cases, we maintain the FIFO ordering in which sends occurred. And so what happens in the platform is that if you send 20 megabytes before you send 10 bytes, it may be that in your mind that ordering didn't matter, but in the low levels of ISIS, FIFO ordering will never be violated, and so the 20 bytes have to wait. So this out-of-band concept is a really good solution to that problem. It focuses on big byte arrays, and that's because we don't really want to even worry about what's in the memory map file. In fact, in the recent work we've done with this, we focused more and more on the idea that those memory map files could come from some other application. For example, if you're a Hadoop user or a MapReduce user, you may well have data in HDFS. That data is a very good example of something which is a memory mapped byte array. And it might be a gigabyte large, it depends on what you're trying to do. And you could have tons of them because that's the way people use HDFS these days. So we assume that these objects to work with are big memory map files, and for things that are internal to our program, for example, when ISIS transfers those process group views I told you about, it just creates a memory map file with a temporary name in /temp, creates a kind of funny view name, fills it in. It's very cheap to do this, it turns out, and then it says, okay, well, here's a memory map file of my own, transfer it to those joining members, and then delete it, and that works. So we can share them, and it's much faster than any form of copying. And in fact, with what's called InfiniBand, which many large clusters have these days, we even managed to do this in such a way that no programmatic access to the data ever has to occur. The InfiniBand device literally DMA transfers the data from your memory map file to the 20 guys who are trying to receive it, and no one touches the data whatsoever. InfiniBand happens to be reliable, and because it's reliable, we can start to talk about giving you 40 gigabit per second, so that would be what, 5 gigabyte transfer rates from one source to even multiple destinations, which is really blazingly fast if you think about it. And that's so much faster than what ISIS itself normally could have achieved that it really is quite an interesting capability. So here's a kind of picture that you might think about, but just for one memory map file. You're going to really want to think about this for hundreds of them at once. But before, we've got machine A, and it's got this object alpha on it. And we've got some other machines where we're running something or other, and we want to transfer it. And what this transfer capability in ISIS is going to give you is the possibility to say, put copies in various machines. And you can use any kind of subset you like. You will need to have an ISIS server of some kind running on each of those machines. We've built such a server. Or you could build an application using the OOB tool. It has to be running on those machines because that's our hook into those memory map file regions, and it will create the file regions that are needed on the machines where we're making new files. And it'll do that dynamically and automatically. So how does this work in total? You've created a memory map file region. It has a name, but maybe even in the /temp area. You put some data in it somehow. It could be your C++ application, which doesn't know anything about ISIS, that did that. Maybe you read it in off a disk, and it could be huge. And our goal is going to be to move that stuff ideally with a single DMA transfer from one source to all the destinations, the fastest that the technology can handle. And so here's the picture again. And we want copies on a couple of machines. So what we do is your application, which could be outside of ISIS, in which case you would use something that we call the command tool interface, and I'm going to talk about that later separately and not in this module, or your program, in which case you're using the ISIS tool library directly and you just make a call to our routine, tells ISIS by registering it, and the registration operation is called OOB register. And so now we know that alpha exists. And we do this in a group context. So there's got to be some group that includes A and B and C and D. And then what will happen is on your application program can tell the replicas you're interested in to fetch X, all right, whatever the object is. I've called it alpha down below, and I should have called it X. X is the file name, and alpha is just sort of representing the region. Maybe that's confusing, and I'm sorry about that if it is. Then what you can do is you tell ISIS itself to use the out-of-band re-replication feature to change the replication pattern of this object alpha. That you want it to be on B and C, but you don't want it on D. And then the applications on B and C have gotten this ISIS reliable message that's come through and said, hey, I'm interested in you touching this. So why did we need that? Well, there is an up call that occurs if you want it on B and C that says a file has arrived. But quite possibly you have to tell them why you sent them this memory map region. And so in your multicast, what you would do is you would say to them, I'm sending you a memory map region which I'd like you to process in this way. Its name is such and such. Please fetch it. Now, OOB re-replicate is going to move the data in the background, and these guys are going to fetch it. And they're going to do that by calling OOB fetch. And what OOB fetch does is it pauses until the file is fully present, and then it returns a pointer to that memory map file region. So there it goes. And there goes the other copy. But in fact, as I said, if it's possible, we'll do it in one multicast, and I really would have shown both moving at once in that case. Oops. And once you've done this, the file's there. And OOB fetch delays you until it's quite sure the file has been reliably transferred and deciphered if it turns out that you asked us to do encryption and decryption before the transfer and after. So the ISIS code could be directly mapped to your application, or it could run in a server that you talk to. And what we've done is we've got a remote procedure call feature for native C++ that lets you call into this. And then the command line feature I told you about that I'm going to do a separate little module on is a C++ program that uses this. And the advantage of that is that for Hadoop users, they would be able to keep their existing Hadoop technology unchanged. And then through these command requests, they could re-replicate HDFS objects really quite flexibly through ISIS and not have to change their Hadoop or HDFS logic whatsoever. All right, so the first step is to register the file name, and you do that in any place where you have one copy. You have to form a process group, and you actually do this registration in a process group. And then the operation that tells ISIS to change the replication pattern is something called OOB re-replicate. It says, I want a different pattern of replication. And then on the receive side, you use OOB fetch, and that gets you a pointer to the new data after the data has fully arrived, because you could manage to talk to the other side before the data has finished being transferred, and so it may have to wait, and then it can have the pointer. So we call this out-of-band because it has this interesting mix of doing communication inside ISIS about the file and moving the data itself sort of outside ISIS through your Ethernet multicast or your InfiniBand transfer. All right? And ISIS is optimized very heavily for speed in this particular case. So as I said, we come as close as we possibly can to just the raw physical speed feasible on the cluster, which can really be surprisingly high. Now, I was talking about using OOB fetch. You always need to do that, but you do have the option of not communicating internal to ISIS. So one other possibility is you can hook an event handler into the OOB system, and then we'll do an up call to a method you provide as each file arrives with OOB re-replicate. So in that version, if you know what to make of a file arriving, if your application automatically has some way of processing incoming files, what can happen is you sort of push the file with OOB re-replicate, and the receivers get told, oh, such and such a file has arrived, and the up call can then start to process the file directly. So we can re-replicate in a flash. Here's an example of the code, and here you're seeing quite how simple it is to create these things, because you may have been thinking, well, this sounds great, but really scary. So if you look at the first line here, the memory map file, create new, this is the Windows.NET interface. There's a different interface for Linux if you prefer Linux. But this creates a new memory map file, and you can see all I needed to do really was to give it the file name, which will be something like /temp/xyz. And the capacity would be how big the memory map file region should be, which would typically be however big you want the file to be. And then if you want a pointer into that, I'm programming in C#, and in C# pointers are considered unsafe. So in C# what you would do is you would create a memory mapped view accessor, and you can see it doing that here, after which this is an example of code that writes bytes into the file. And there's actually a byte copy routine that's quite efficient, and there's some other ways to do it. And if you're doing this on Linux, you can easily set this up so that no copying occurs at all. For example, you could create the memory map file and work with your file region as the big byte array for your application, or huge array of double precision numbers, or whatever it is you're doing, and you might never need to copy in and out of it ever. So people with very big scientific computing applications these days often take that kind of an approach. You can also map an existing file. So OLB re-register doesn't really require that you created this memory map file fresh the way I did in the stop code. If the file name already exists, Linux and Windows will automatically preload the data from the file into that region. And so the code would look the same, and you wouldn't even have to do the initialization I'm showing here. And this initialization, by the way, if you're wondering, just puts numbers 0, 1, 2, 3, whatever, into the bytes of the file. It's got nothing else in it, but it's just a pattern of data. So then after that, you call OLB register. You can see the call here at the bottom. The string file name should be the same file name that we used up above. And the memory map file pointer is this object that came through from the original create new. You see? The MFF create new. So it creates a new object. In this particular case, I wanted an accessor because I'm in C# and I want to put some data in it, and then I do. But you might be able to skip that step in many cases if you were mapping something that already had what you wanted, and then we're able to re-replicate it. So this re-replicate, now what it does is when you have a file already registered, so you had to do the OLB register first, you can give a list of locations where you would like replicas. And the only rule on this is you have to have a process group that those locations are members of. So you have to have a program running at each of those places, and the program instances have to join this group, and now you've got a group, and now any subset in that group can be used to create this list where. So what goes in there would be the locations, and if you, for example, if you're focused on that you know the machines by IP address, you can go into the ISIS addresses in the view, and you can see which of these processes is at the correct IP address, because an address has a home field in it, and the home is an IPv4 internet address. So what an ISIS address contains is the host address, and that would be your, and then a process ID and some port information, which you wouldn't be interested in for this purpose. So the where argument is actually a list of addresses, which you could form by looking to see where you're trying to put the file and seeing who the representatives are at those locations. In this example here, v.members.toList would be an example where you take all the members and turn them into a long list of addresses. And then when you give this to OLB re-replicate, it makes the replicas at those locations. And the only rule is this. It's going to delete replicas that are at locations which aren't in the list. So be a little careful of one thing. You can't re-replicate a file in one step if the outcome has the file at totally new locations. You would have to do it in 2 steps. First, change the replication pattern, then delete the old copies. Because if you ever went through a period where you're re-replicating and you've deleted the old copies, but the new ones are supposed to still be created, in that situation, ISIS will notice that there's an error and it will throw an exception. So once it knows about the file, you can call OLB re-replicate. Here's the other way to call OLB re-replicate, file name where, and in this version, you get an upcall when the re-replication event has finished. So because this transfer is happening outside of the normal ISIS system, it can take a while, seconds maybe, for multi-gigabyte files. It could easily take seconds. And so you can get an upcall that tells you when the action has terminated. And this is illustrating how to do that. The upcall here is this delegate that's shown, and it's going to get told what the file name was and also what that memory map file region pointer was. In this particular case, it just prints out a message which goes into the ISIS log file and onto the console. And the type signature shows up on the previous line, and that's what the action is. In C#, delegate turns out to not have an automatically inferred type signature. So whenever you use the word delegate, you're always going to see me putting the type signature this way first. So in effect, I'm casting it. And the delegate method will be called when the transfer itself is done. And then once you use OLB fetch, you get back one of these pointers, and you can then turn that back into a view accessor if you want access to the bytes. So here's a typical call to OLB fetch. This will be one of the other replicas. He's been told somehow to go and fetch that file. And so he calls OLB fetch. That might pause for quite a while because of the transfer, but then it comes back and says, here's a pointer to that region. And at that point, you could access the bytes themselves if you want. You see? It'll wait until the action is finished. And do be careful about this issue of not wanting to leave an ISIS-owned thread jammed up on this call for long periods of time. So when ISIS delivers multicast to you or point-to-point messages, the thread it does that on must be free to continue doing new ISIS operations. You can do a little computing, but things like this that could block for many seconds, you must not do these operations on that thread. So if you're going to send people a multicast that tells them call OOB fetch and then do something with the file, fork off a thread that does the actual call to OOB fetch. So we created a server that uses this, and the way that we did the command line stuff is that we built this server that's designed that you would run it on each of a set of nodes in a cluster, and then we built a small RESTful style of API where we could do procedure calls from outside the server into it, and those procedure calls are just versions of OOB register, OOB re-replicate, and OOB fetch. And so in this way, from outside of the ISIS system, we can ask it to do things. And because we're talking about memory mapped files, those files can actually be shared between our server and your application. So you can now have a C++ or a C application or something else that creates this memory map file and then tells our server to map the file and send it. ISIS never needs to see the bytes in the file. It just needs to know the file name and can transfer the data using the hardware DMA features of the network interconnect, which is as lightweight and as fast as one could possibly be. So here's a recap. We've got a file somewhere on machine A. We form a group. I didn't show the group here, but these guys have to be in some form of group, or at least you have to have an ISIS server on each of the nodes in the background that forms that group. We tell that server to register the file. We send a multicast or something that tells BNC to fetch the file. Re-replicate changes the replication pattern, and it's done concurrently with that. And these other guys call OOB fetch. In the background, the file gets moved, perhaps step by step, or perhaps if multicast is available directly in one operation, and we're done. And as I mentioned earlier, we use OOB transfers now within ISIS to transfer initial group views when a whole batch of members join all at once, which happens especially if you use the master worker model that we talked about in one of the earlier modules. They all need the same view, so we write that view into a memory map file region, and now with the OOB re-replicate, we're able to transfer it to all those members without kind of congesting the internals of the ISIS system by trying to send that data point to point to 55 members perhaps that are joining all at once. You can use it for state transfer too, and actually I recommend that. So if you have a group that has a very large state, like gigabytes, maybe your group is managing some kind of a data service, do consider using OOB file transfers to pre-transfer the state of your group. We talked about that a little bit in the module on ordering, even though it's not exactly an ordering topic. But we did talk about state transfer in that context, and as you may remember, what we recommended was that if a group had a very large amount of state, you didn't want to lock the group down, synchronizing the state transfer with relatively to multicast before or after. And so by using the OOB transfer tool, you can transfer this large amount of state first, before these guys have even joined your group. Now, because OOB requires a group, you would have to have a helper group that you would build a separate group that the transfer could occur in. However, that can be done easily. You just create a second group. You see, ISIS does allow you to join multiple groups. It just doesn't recommend that you do thousands of them. Here we would just have one helper group. So you can have an OOB group in your application for the purpose of pre-transferring state. And then once it's been transferred, the join would send over an indication of how much of the state you've already got. And then the state transfer can learn that number from the join. It shows up in a field called v.offset in the view. And so you create a checkpoint starting at that offset, covering the delta that's been added to the group since, and you end up with a very efficient solution. And so the out-of-band transfer solves a problem which would otherwise have caused the group to be running and then pause while a gigabyte of data is transferred and only then resume. And that pause would have been very, very disruptive to applications. This lets you load balance the roles. And in fact, you can load balance other kinds of roles as well for this type of state transfer. One possibility I should comment is that ISIS does have this nice client API, which would be a good way to get in touch with the group to request the transfer before you're in the group, because there is otherwise this issue in ISIS that you can't easily talk to processes that are in ISIS but not in any group that you're in. The one feature that lets you do that is the ISIS client API that we talked about when we discussed the basics in the system. Now, if updates are active, you can get a bit of a race condition where you're transferring data, but updates are changing it during the period of the transfer and it becomes stale. And this is why you might really need to think through how are you going to represent the notion of the time at which the out-of-band transfer occurred was, and how are you going to keep track of the delta in order to send that delta at the time that the join really takes care of. All right, so you're going to use this version of join that takes a timestamp in, but you're going to have to implement that notion of a timestamp. And then the state transfer is going to conclude just the updates that need to be sent, but you're going to have to implement a mechanism for tracking those updates and sending just them. So here we can see it as a picture. P and Q have some very, very large state. We want R to join. R becomes a client of the group and makes this request. Now there's a second group not shown, some form of helper group in which we can do OOB transfers. R is in that helper group. It didn't have any state really, but it was just used for the purpose of OOB re-replicates. And so now P is able to do an OOB re-replicate, and it's transferring this gigantic piece of state at time 1, 2, 3. Now meanwhile, updates are still happening in the main group. Eventually the transfer has finished, the OOB fetch is done. Now R can join the group. It should have said 1, 2, 3, not 1, 2, 3, 4, 5, I guess. Or maybe it's the big arrow that has the wrong number on it. But anyhow, so R says join, and it specifies how much state it already has, and that allows P to say, oh, he just needs the delta since time 1, 2, 3, 4, 5, and it transfers just those elements that need to be updated. And you'd have had to figure out how you're going to represent that delta and how you're going to be able to generate that state transfer checkpoint. But it's a pretty simple thing to do, as you can see, and it takes full advantage of out-of-band transfer for the gigabytes, so you get a much faster join than if you tried to do that straight through ISIS with a normal checkpoint that contained all the data. Okay, and there's the updates going. And the obligation on the group is somehow to have a representation of updates during that brief period after the OOB transfer was done until the join occurs. And during that period, you're going to need to have some kind of a log of updates that were received. Now, I want to comment that there are several ways to create byte array representations of data, but they do involve copying, and be aware that when you work with managed languages like C#, Java, you do have this difficulty that even a thing like a byte array is in a representation which you can't directly use for the OOB transfers. So even though you've got a thing called a byte array, you still are forced to do some copying. So there's several ways to create these byte arrays, but what happens is that you start with your object representation of whatever it is, and then you create a byte array, and then you're forced to copy it into the memory mapped view accessor. So OOB isn't a panacea. It's a good way to avoid congesting the lower levels of ISIS, but it doesn't really eliminate all copying unless the data was already in a file in the first place. Because these things that you're creating, whether it's with the message to be array routine or C# serialization or something else, all of them create a byte array object in C#, and you would then have to copy that through the MVA thing that you saw in the first slides into the new region of the memory map file. But that copying can be very, very fast, really. So I've already commented on this. I'll just remind you that the fastest way to get data is a DMA transfer that uses an Ethernet multicast or InfiniBand, and that's what ISIS uses. The worst case for ISIS would be that you use OOB, but you've locked ISIS into its unicast-only mode, and it doesn't have access to some kind of fast transfer feature at all. In this situation, ISIS won't congest in the way I described, but you won't get the full benefits of the out-of-band transfer. So there are types of platforms where the OOB infrastructure isn't going to be as beneficial as it would be if you're not forcing ISIS into this unicast-only feature. We're looking into that, and what I've just said may actually not be true a year from now. But today, you'll find that to really get the blazing speed of the OOB transfer, you're compelled to use ISIS with this unicast-only feature turned off, which is the default, but that may mean that, for example, on Amazon EC2, you won't be able to take full advantage. The feature set will work, the API will be fine, but the speed won't be nearly as good. So thank you, and we'll tackle a different topic in the next module.